Enjoy! Okay, let's begin. Integral as antiderivative of a function. Consider the following tables. If I have a function denoted by f capital X, and if I have derivative function is denoted by f capital accent X, and then this function is x squared. In the last meeting, we have learned about derivative. So if I have a function x squared, I have a derivative 2x. And then if I have x squared plus 2, this derivative is 2x. And then if I have x squared minus 4, the derivative is 2x. And then if I have a function x squared minus 17 over 3, I have the derivative 2x. And if I have a function that is x squared plus c, where c is any constant, I have a derivative function is 2x. If we observe, we can see that all the function f capital X are antiderivative of the function f capital accent X is equal to 2x, while the function f capital X has different constant. Okay, this is different constant. It can be shown that the function f capital accent X have a multiple antiderivative. We can conclude that integral f capital accent X dx is equal to f capital X plus c, where c is any constant. So this is a concept of integral as antiderivative of a function. For more details, we must understand about the basic formula for indefinite integrals. If f capital X is a function with f capital accent X is equal to fx, then integral fx dx is equal to f capital X plus c, where c is any constant. For n is rational number and n is not equal to 1 with a and c is real constant, then it applies integral ax to the power of n is equal to a over n plus 1 times x to the power of n plus 1 plus c, where c is any constant. Now, to more understand, we will prove the basic formula of indefinite integral. Okay, now we will prove integral ax to the power of n dx is equal to a over n plus 1 times x to the power of n plus 1 plus c, where n is not equal to 1 and n is rational number, and then a and c is real constant. So consider the following tables. First, I have derivative, and second column I have antiderivative, and then this is pattern. Okay, if I have the value of derivative is 1 and then the value of antiderivative is x, so we have the pattern. This is 1. Can we write 1 times x to the power of 0, and then x is 1 over 1 x to the power of 1. So we have pattern that 1 over 0 plus 1 times x to the power of 0 plus 1. Second, if I have the value of derivative is 2x and then the value of antiderivative is x squared. So we have pattern 2x can write 2 times x to the power of 1. and x squared can be written 2 over 2 times x to the power of 2. So we have the pattern 2 over 1 plus 1 times x to the power of 1 plus 1. And then third, if I have the value of derivative is 3x squared and the value of antiderivative is x to the power of 3. And then we have pattern x squared, we can write here, and then x to the power of 3 can write 3 over 3 times x to the power of 3. Why 3 over 3? Because this coefficient is 3, so we can write 3 and not changeable the value of antiderivative, so we can write 3 over 3 times x to the power of 3. This pattern is 3 over 2 plus 1 times x to the power of 2 plus 1. As well, if I have the value of derivative is x times x to the power of 3 and I have antiderivative is 2x to the power of 4. So we have pattern 8 times x to the power of 3 and x over 4 times x to the power of 4. So we have pattern 8 over 3 plus 1 times x to the power of 3 plus 1. And then if I have a derivative function is a times n times x to the power of n minus 1, and then I have value antiderivative is a x to the power of n, we can write the pattern a n over n minus 1 plus 1 times x to the power of n minus 1 plus 1. You can see that a n x to the power of n change to n, so we can write n minus 1 plus 1. This value is n. And the last, if I have the derivative is a x to the power of n, so we can find the integral of a x to the power of n dx is a over n plus 1 times x to the power of n plus 1. Okay, this is a pattern of derivative and antiderivative relation. So we can conclude that integral a x to the power of n dx is equal to a over n plus 1 times x to the power of n plus 1 plus c. Okay, thank you for watching this video. May be useful. Wassalamualaikum warahmatullahi wabarakatuh. Bye bye.